Ladies and gentlemen, welcome everyone. I am Dr. Roland A. Drolet, PhD in Biomedical Engineering from the University of Toronto, 1971. I am the developer and inventor of the RUMART PEM system that has helped over 1 million people all over the world who were suffering from all kinds of health problems. Okay, so here is the Einstein Nobel Prize 1912. How he got his Nobel Prize is not from his relativity theories, including the general relativity, but it's from a simple experiment trying to really validate what Max Planck, who invented quantum mechanics, because the Planck's constant has been named by himself, and Planck's trying to explain the spectrum emitted by what we call black body or constant body temperature. There is a spectrum of energy emission or a wavelength. So he defined this little energy pack of what he called a photon to explain the spectrum of a black body emission. But he thought that it was just a mathematical trick or trickery to get the right answer, because classical mechanics could not explain the spectrum of electromagnetic energy emission, okay, of a black body or constant body temperature. So this is the simple equation that Einstein used, and he used a metal and shining or directing light, let's say visible light for instance. If the photons have enough energy, then it will take electrons out of the metal. We know that in metal, because it's conducting electricity, there are electrons in conducting energy band, that we call. So he took some of the electron out with shining light and measuring the kinetic energy of the electrons. He could check this little equation, really, to just introduce it. You have the kinetic energy of the outcoming electrons given by the incoming energy of the photon minus what he called the work function. This is the electrical energy needed to take the electron out of the metal, which is given by the simple formula: the charge of the electron times the voltage, let's say like a voltage barrier, okay? But if the energy of the incoming photon is less than the work function, the energy to take the electron out, there is no electron coming out. So you realize no matter what is the intensity of a photon, if the energy is too little, there is nothing coming out. And so that's how he validated this energy pack of Planck's with classical concept of kinetic energy, and he won the Nobel Prize in 1912 for that. Okay? Now we are going to show you, I am going to show you how a solid becomes liquid. Okay? So whether it's a metal or all kinds of solids, we've seen in the previous sheet the energy pack of a photon, electromagnetic photon of light, for instance, but it could be any frequency, not only visible light. So we have the Planck's constant multiplied by the frequency here, it's not the electromagnetic frequency, it is the mechanical resonance frequency from classical mechanics. We call it Einstein's frequency because he defined the mechanical resonance frequency of an atomic mass, for instance, which has which is in a metal, let's say, or in a solid, which vibrates because of the temperature. We see that at any temperature there is a vibration energy we just mentioned earlier. So the vibration energy at temperature T is given by the Boltzmann constant multiplied by the temperature. When this vibration energy is equal to what we call a phonon, because this is not a photon, it is, but the same Planck's constant and a mechanical vibration energy, then when this thermal energy is equal to the vibration of the atoms or molecules, then the solid breaks down. So in the formula of the Einstein frequency here, we have 1 over 2 pi square root of the elasticity constant multiplied by what I call here delta R, the elongation between the atoms. For instance, if it's about 2 times the radius of the atom in a metal, then the metal breaks and it becomes a liquid. So when the square root of this time constant here, the Kas here for atomic spring constant is simply the Young's modulus of solid state physics. So this is measured by simply elasticity experiment trying to elongate a metal in Newton per square meter. So this is known, knowing the about taking, for instance, 2 times the radius of the atom, which is about 2.5 angstrom for almost every atom except the smallest, then we get this Einstein frequency, and the temperature at which the metal will liquefy, or you get liquefaction, is given simply by taking this Boltzmann constant here, so it's Planck's constant time Einstein frequency divided by Boltzmann constant that is known in statistical physics, and then you get the theoretical temperature at which the metal will melt. It will become a liquid. Okay, so then of course if the temperature of a liquid is reduced, then it will solidify. Okay, so that's about the explanation of this quantum phonon related to the vibration energy. Okay, here we have seen this image before, so it's just to show you that, to remind you that in electromagnetic field, the wavelength multiplied by the resonance frequency is always equal to the speed of light. Okay, we have explained earlier that the electromagnetic wave travel freely in vacuum without resistance. Now I just want to show you here that really this is related to the electromagnetic energy of the Raman system, the pulse wave and all that, and that the ray or the radius in this equation here that we have seen earlier is just given by the speed of light multiplied by the time constant of Raman here, which is given in the Raman patents, and here you have page 59 and 60 of the US patent, as a matter of fact, that you should see in this video. Okay, here you see the classical definition of angular momentum. For instance, it could be the mass of a planet, its velocity around the sun, and the radius, average radius of this distance between the Earth and the planet, rather, okay? It's not the radius of the planet. So the angular momentum, it should be ANG for angular, is the mass times velocity times the radius. For a photon, with the definition I've given in my little theory, the radius of the photon would be its wavelength divided by 2 pi, and a wavelength being 2 pi times the radius. So we would have for a photon simply the mass of the photon that I define would be the energy pack divided by c square. Remember, mc square is the energy. So the mass of the electron, or equivalent mass, would be hf divided by c square. The speed of the photon is the speed of light, okay? And I put it there, here rather. And now, what is the radius of the photon? I've defined it as the wavelength of the photon divided by 2 pi, but the wavelength is c over f. So when you multiply this, you realize that the two c's there cancel, the f cancel, so the angular momentum of a photon is simply h over 2 pi. That is symbolized by h with a line here. It's h divided by 2 pi. So no matter what is the frequency of the photon, for any photon of energy, electromagnetic energy, the angular momentum is simply h divided by 2 pi, always the Planck's constant. Now for the electron, in the Bohr model of electron, we have a little formula for the radius of on the nth orbit and the velocity. So if we multiply the mass times the velocity times the radius, we simply get n times h with a bar, so that's nh divided by 2 pi. So that's interesting, and that's how Heisenberg developed his uncertainty principle, because electron has to go on one orbit or the other. It cannot stay in between. Okay, thank you. Here we see the definition of magnetic momentum. We talk about angular momentum. The magnetic momentum of nearly everything is defined by an electric current going around a certain surface, and the magnetic moment will be perpendicular to the surface. So if you have an electric current circulating here, you have a surface, the magnetic moment will be perpendicular to that, okay? So if we take the case of the electron circulating around the nucleus, we take constant charge as the charge of the electron. dt is simply the time it takes to go around. Without going into all the details, using the Bohr model of the atom, we reach the value for the Bohr magneton, which is around 9 point something, 10 to minus 24 ampere per square meter. Okay. Now this magneton, it's a unit of momentum, of angular momentum. When we talk about, or magnetic momentum rather, when we talk about nuclear momentum, it is defined by this magneton here divided by about 2000, which is the ratio between the mass of the proton and that of the electron. Now, when we place a little magnet perpendicular to the field in the Rumard rings or near the rebound, we see that there is an alignment force between the field and the little magnet. So this is given by this equation involving magnetic moment and the magnetic field. Magnetic moment of the magnet and the magnetic field perpendicular, which will give the maximum force to straighten it on the vibration. Now here, here, I just want to mention that we have a simple equation. This is a term angular momentum. There is a relation between angular momentum and magnetic momentum, which is simply given by multiplying it by the mass, the ratio of the mass over the charge, and divided by what is called a lambda factor in quantum mechanics, so that theory agrees with experiment. Okay?